Okay, so in the matching, first of all, on your here on your review, you have this table on number 4. It says, name each of the following, blah, blah, blah. So you write the name. The properties, those are properties that we've taken within that group properties table that we did. That's like 1A. That's Roman numeral 1A. And then the most common properties, soft, silvery, metals, reactive with water, whatever. And then it has the most common ion. If you will all please take a look for the transition metals, which is 3 through 12. It's that middle block in there. They do not have a most common ion, so that is varies, V-A-R-I-E-S. It's variable depending on what it is. So it is varies.
Middle block.
That's crazy.
That is for the middle one, middle row, yes, all the way to the right.
The right column.
Right column, varies, yes, V-A-R-I-E-S. Yes, V-A-R-I-E-S. I think there might be some on my desk. Any other questions? Okay. So does anybody have one of these matching ready for me? So do you have one for me that you can tell me?
Number 5 is C.
5. Energy, ionization energy. Yes, ionization energy. Ionization energy is the energy required to remove the most loosely held electron.
Are we allowed to use this one?
All right. Anybody have something else for me? Take a look. Some of these are pretty obvious. Talon.
Is it H?
Electronegativity. The ability of an atom to attract electrons. Yes, that is H. Oh, why is that doing this? Why? What did it? Hold on. Hold on. Let me get here. This is ionization energy, we said was C. Electronegativity, we said was H. 9. Ionic radius. The radius of the most common ion. Yes.
Number 8 is F.
Atomic radius. The half the distance between nuclei of a bonded atom. That would be correct.
Wait, did someone say number 7?
No. Electron affinity.
11B.
11B. No.
Oh, wait.
7E.
7 is B, yes. 12. D, shielding, decreases the pull of the nucleus, yes.
Wow.
11 is E, yes. Nuclear charge is the number of protons in the nucleus. Oh my gosh, yes, Captain Obvious. 10 is A. We are going to come back to these, so make sure that you have that handy. Any questions over that? All right, let's go. All right. Please pay attention. All right, so one of my handiest things that how I remember all these things when I'm thinking of the periodic table is, first of all, we have francisium down at the bottom. All right, and then over to the top is helium, but I like to use fluorine. So when I'm thinking of the periodic table in size and all of this information, I think of Fat Frank. So Fat Frank, way down here. And then up here is fluorine, and I call her Skinny Flo. Okay? So Fat Frank and Skinny Flo. I always have that in my head when I'm thinking of these things. FR for Frank, yep. All right. So we are going to put some arrows in here. Why? Because we're going to get to it. He's the biggest atom on the periodic table. So I call him Fat Frank. It's francisium. Huh? Fat Rick. Well, I say fat. Well, I use FR for Frank. So Fat Frank. And then FLO, Flo, skinny fluorine.
Wait, so why do you have those then?
That, you'll figure it out here in a minute. All right. Effective nuclear charge. So as I go across the periodic table, we are increasing protons, right? We are increasing protons, which means what happens to our nuclear charge as we... It increases. Because nuclear charge is doing what? Increasing. Why is nuclear charge increasing? Because we have added protons. This is my why. These things I'm adding in there, those are my whys. While shielding. So as I go across a period, do we add any shells? Do we add any shells across a period? As I go from sodium to chlorine, am I adding any energy levels? No. So shielding remains constant.
Is this review going to be for grade?
Uh-huh. No added energy levels. So my arrow, above my arrow over here going across, I'm going to put an I. So I know that that means increasing. Now, effective nuclear charge does what down a group? So how does my nucleus affect those electrons out on the outer edge? What happens to my effective nuclear charge as I go down a group? It decreases. It decreases because although we have added shells, and we've added more protons, but we have moved further away from the nucleus. Okay, so it decreases, effective nuclear charge decreases because of added energy levels and shielding. So my arrow is a D over there for decreasing. So here's where Fat Frank and Skinny Flo really come into play. Atomic radius. As I go across the period, as I go from here over to here, as I'm going towards fluorine, what happens to the atomic radius size? The atomic radius is going to decrease. And it decreases because of we have more effective nuclear charge. Because we have more effective nuclear charge, we have more positives inside that nucleus, we're able to bring those electrons in. And I call it tightening up the belt. We can have more notches in there, we can tighten that belt up. Okay? So we get skinnier as we go towards fluorine. Now, what happens to my atomic radius as I go from lithium down to Fat Frank? What's going to happen to our size? We're going to increase. And we increase because distance from the nucleus increases. And that is all because what have we done as we've gone down the periodic table, down a group? What have we added? Energy levels. Any question over that? So this is kind of like that graphing activity you guys did in the other day. Okay, everybody good before I go to the next one? Next, somebody read me the definition of ionization energy. What is ionization energy? Anybody? Somebody yell it out. On your period, on your matching. What is ionization energy?
Energy required to remove most loosely held electrons.
The energy required to remove the most loosely held electron. So, ionization energy. The amount of energy required to remove that loosely held electron. So, as I'm going across a period, then what do you think is going to happen to my ionization? Is it going to increase or decrease? Is it going to be easier to pull electrons away from over here or over here? Over here? Why?
Wait, it's gonna be but wait, is it just pulling electrons off?
Just the amount of energy to remove one electron.
It's gonna be
So it's going to be easier to move it away from over here, right? Okay. So that means as we go across a period, ionization energy is going to increase. It's going to be harder to pull those electrons away. It's going to take more energy to pull those electrons away because we have increased effective nuclear charge. Now, as I go down a group, so if I'm going down a group, I'm going from lithium to fat frank, which is going to be easier to remove from, lithium or fat frank? Who's going to be easier to steal an electron from?
Probably fat frank.
Probably fat frank. So it is going to decrease down a group. The energy decreases down a group. So easiest one to steal an electron from, fat frank. The hardest one, besides the noble gases, is fluorine. It's going to take lots of energy to steal that first electron away. Again, because the distance from the nucleus increases. So we have shielding. Fat frank can't see those outer electrons, so it's going to be easier to steal that one away. So we have increased shielding and energy levels. Questions on that? Okay. Somebody give me the definition of electronegativity. Flip over your thing and give me the definition of
The
electron.
electron has a negative charge.
What is it, Talon?
Wait, electron.
Electronegativity.
The ability of an atom in a compound to attract.
The ability of an atom in a compound to attract electrons. So this is the ability to steal those electrons away. So who do you think is going to be easier? Who's going to want to steal electrons? If we're looking over at the periodic table, is the Right-hand side or the left-hand side? Who wants to steal electrons away? If we're looking here, the right-hand side. This is right. Right? Right-hand side. So electronegativity is going to increase across the. If they want to steal electrons, then it's going to be hard. It's going to take a lot of energy to take their electrons away. Okay, so these two do the same thing. So it increases across a period because of increased effective nuclear charge. And it's going to decrease down a group because our distance from the nucleus increases. Again, this is because we have shielding, more shielding, and more energy levels. Any question on that? We are almost done. And then we're going to practice a few of these. All right. Ionic radius. So ionization energy and electronegativity do the exact same thing. The trend is the same way. Increasing this way, decreasing that way. Ionic radius does the exact same thing as atomic radius. As we go across a period, what happens to our size? Our size decreases across a period. Someone tell me, cations, positive or negative? Anybody know?
Positive.
Cations are positive. Anions are negative. Ionic radius for both cations and anions are going to increase down a group because distance from the nucleus is increasing. All right, again, decreases because of effective nuclear charge. And then this is increasing because of shielding and energy levels. So some added notes there. A cation is a positive ion, whereas an anion is a negative ion. Compared to a neutral atom of itself. So I'm going to draw a neutral atom of lithium. So if I have lithium with my 3 protons and I have my 3 electrons, this is a neutral atom of lithium. All right. A cation of lithium has done what with its electron? It's lost an electron, right? So when it loses an electron, what happens to its size? It shrinks. The size gets smaller. So a cation is smaller than its neutral atom. And that is because we have lost and energy level. Okay? So a cation is positive. It's smaller than a neutral atom because it has lost an energy level. Now, if I were to do the same thing and I were to draw 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. If I were to draw oxygen, 1, 2, 3, 4, 5, 6, 7, 8. All right, oxygen, when I draw its anion, what happens is it gets larger. Okay, so an anion is a negative ion which is larger than its neutral atom. And why? Why do you think this got larger? We didn't add a shell. What could possibly make it get larger? What did we add there? Electrons. And electrons have what charge? Negative. And when I have a negative charge and I add it and I get it closer to another negative charge, what happens? What? Negatives do what to negative? It's not math. Negative plus a negative don't make a positive. Negative, a negative magnet and a negative magnet. When they come together, what happens? They go apart. They repel. Because we've added more electrons in here, they start to repel each other. So they get larger than the neutral atom because we added electrons. Which causes repulsion. Okay? So we've added more negatives in there, so they're going to spread apart from each other. That question 6 on there, what's it say? What? Okay, so the varying characteristics of the deep rock, and that is because there are so many characteristics of the D block, and it's because there are a variety of metals. There are a variety of metals. So there's a bunch of different types of metals that give them the different characteristics. So you need a periodic table in front of you. We're going to do some problems, and we're going to popcorn it. So I'll choose the first person, and you get to choose whoever. What? You'll know what's going on. Get a periodic table in front of you. Make sure you have those arrows. Those arrows we just drew. Your test review with the arrows. Huh? Huh?
Should I wait until we finish all this?
Yeah. Everybody ready? Okay, so I am looking for the metal. And my choices are lithium, which is number 3, silicon, which is 14, and sulfur, which is 16. So looking at your periodic table, I want desk number 15. Is that you?
It's like 3-1.
No, what about the other label?
Oh.
Oh, it is you.
Yeah, it is.
Which one is a metal?
Right. So, C.
Look at your periodic table. Look for Li, which is number 3.
It's
Somebody have?
LR.
No,
It's Li. Everybody know how we found that? You should have your periodic table. You have your metals and your nonmetals, and you have your metalloids. Your metalloids separate your metals from your nonmetals, or your semi-metals. That's stair step. Huh? What? Just the metal. Silicon is a semi-metal, and sulfur is a nonmetal. Look, everybody, periodic table. See the stair step? Everywhere to the left is metals, right is nonmetals. That's that right there. That defining area on my periodic table is a stair step. We have way more metals than nonmetals. Okay? All right, so smallest ionization energy. Who is going to be the easiest to steal electrons away from? We have nitrogen 7, phosphorus 15, and arsenic 33. Choose somebody. Russell. Look at your periodic table. Who is going to be the easiest to steal electrons away from? Easiest. 7, 15, 33.
Throwing it out there, 33.
Throwing it out there, you're right. All right, largest atomic mass. I'm looking at 19, 20, and 21. Popcorn it somewhere, Russell. Choose someone. Oh, pretty sure he's looking at JC.
Yeah.
She's avoiding it.
I was, yes.
Largest atomic mass out of 19, 20, and 21. Scandium, yes. Member of the halogen family. So we have 16, 17, and 18. 16, 17, and 18. JC, choose someone. Abby. Chlorine. Any questions over those? All right, we've got 10 more to go.
Let's go. Oh, snap.
Oops.
I'm guessing a lot of the tests are left open.
All right. Gallium, which is 31. So I'm looking at 31, 13, and 14. Largest atomic radius. Abby, choose someone.
Sarah.
Sarah, largest atomic radius out of 31, 13, and 14. Atomic radius.
Oh, here, sorry. Since the largest, it decreases periods, so largest would be, right?
We decrease and increase this way.
Oh, okay, so it's the GA.
GA. Largest atomic number, 23, 41, 73. Sarah, choose somebody. Vanadium, Nebidium, and TA. Largest atomic number. Number 23. They're right underneath each other.
Oh,
TA. All right. Member of the noble gases. TEI or XE. Allie, choose somebody. XE.
We easy that one.
4 energy levels. SI, GE, or SN. So we're looking at 14, 32, and 50. Who has the 4 energy levels? Georgia, choose someone. Cade.
Hold up. SI. No, hold up.
4 energy.
You said 4? Oh, GE. She was lying. How we get the third one?
Member of alkali metals, Libe or B. So 3, 4, or 5. K, choose somebody.
Shoot. Tyler.
Lithium.
Lithium. Any questions over that? All right. Last bit. 6 valence electrons. We're looking at 33, 34, 35. Tyler, choose somebody.
Ryan.
6 valence electrons.
That's a funny. That was me.
Ryan, I'm sorry. Ryan, I'm sorry.
All right. Non-metal. Hydrogen, lithium, sodium. Ryan, choose somebody.
Which one?
Hydrogen, lithium, or sodium. Which one's a non-metal?
Hydrogen.
Hydrogen. Evan, member of transition metals. So choose somebody. Mercury. So we have 80, 81, and 82. Enrique. 80, 81, and 82. Look at your periodic table. 80, 81, and 82. Member of the transition metals. Hg. Electron distribution ending in S2P1. Sodium, magnesium, and aluminum. Enrique, choose somebody.
Which one?
Oh, Reichel. 11, 12, and 13. Which one ends in S2P1? S2P1. Who ends in P1? In the P block. Who's in the P block?
L-I or A-L?
AL. And lastly, will P82, 83, 84. Who is a metalloid? Choose somebody. Her. Michelle. Who is a metalloid? Semi-metal. Out of 82, 83, 84.
Why are you like this?
This is the second one. Let's see how many more she can do.
Hey, that's the second one in 2 days. That's was polonium. Any questions? Please stop before I come over there. Any questions? All right. The rest of your time is working on your test review.